Hello, welcome back to Math 152. This is the second video on complex numbers. Now, in the first video, we give a very short introductions on why we need complex numbers. There are many reasons why we need complex number. The one I gave was just one of the reasons. And we look at the definition of complex numbers. Complex numbers are all the numbers that can be written in the form of a plus ib, where I squared is equal to -1. And then we talk about the arithmetic of complex number, which means how do we add, subtract, multiply, and divide complex numbers. And while we are talking about the division of complex number, we introduce the concept of a conjugate of complex numbers. So a complex numbers multiply its conjugate is going to be a real numbers, because conjugates and the complex numbers, when you multiply them, the I square, all that thing will go away. So there will be no I, and that is how we exploit them in order to help us to do divisions. And we talk about the concept of putting complex numbers on a diagram, and that diagram is called the Argand plane, the Argand diagram. So every complex numbers can be represented as a point on the Argand diagram. And then, very importantly, we learn how to put all this complex number into the polar form by introducing something called the modulus, which is a fancy name of the basically the magnitudes of that complex number, and the angle theta, which is called the argument, and that's where we stop right there. Now, in the second part of the video, we are going to look at the benefits of putting complex numbers in polar form. So if you have a complex number in polar form, say for example in this case you have a complex number z1, and this is a polar representation. So we have r1 here as the modulus and theta 1 here as its argument, and we have another complex numbers, let's call it z2, and the modulus of this complex numbers is r2, and then the arguments is theta 2. Now, so when we multiply them together, so r1 and r2 here will be multiplied together, and then this product, if you distribute, so when you distribute this, let us look at how do we get the terms that is no I on it. So this is one way to get a terms that is no I on it. So you will see cosine theta 1 here, cosine theta 2 here. Now, another way to get something that doesn't have I on it will be this terms multiply this terms. So when you take I sine theta 1 multiply I sine theta 2, the I and I will multiply together, which gives us I squared, which is -1. So I will be gone. Right, so if you do that, you will see that you have sine theta 1 and sine theta 2, and with the minus sign, which is coming from here. Now, this is the one that has no I on it. When you do distributions, how do you get I on it? So one way is to do this. This is how you get an I in front of it, which is, so this product will give you sine theta 1 and cosine theta 2. Another one to get I on it will be this product right here. So right here, you will get cosine theta 1 and sine theta 2. These are the two different products that will give you I in front of it. So if we rearrange them like this, you will see that this part here looks very suspicious because we have seen it before. So you have cosine, cosine, sine, sine, theta 1, theta 2, theta 1, theta 2 with a minus. This is actually cosine theta 1 plus theta 2. Remember, cosine is a weird guy where every time when you have a plus, you will have a minus. And then it will be so full of himself, he will repeat himself, cosine, cosine, then only sine, sine. So that's like some of the ways you can use to remember that this is actually this. And here you will have sine, cosine, cosine, sine, theta 1, theta 2, theta 1, theta 2. And this is exactly what sine theta 1 plus theta 2 is. So what it's telling you is that when you have z1 and z2 in polar form, so when you have it in polar form and you multiply them, you just simply have to multiply their modulus together, and then instead of multiplying, you just sum up that two angle. That's what happens to the multiplication of two complex number when those two complex numbers are in polar form. So we can do the same thing and realize that the divisions is also almost the same. When you divide two complex number in polar form, you will get the modulus in this form, and then the theta, so the arguments, instead of getting the sum, you will get the difference. So that is how you do divisions when your complex number is already in polar form. So for example, 1 plus I has this polar representation. Square root of 3 minus I has this polar representation. So when you multiply them, you just have to multiply their modulus. That's how how you get 2 square root of 2. And then for the angle, you just have to add them up. So pi over 4, so pi over 4 plus minus pi over 6, it will give you pi over 12. And that is why you see that we have this and we have pi over 12. So if you want to do divisions, and you already have the polar representations for these two complex numbers, so you would take the ratio of these two numbers, and then here, instead of adding, you would subtracting. So you have pi minus over 4 minus pi over 6. That is how you get 5 over 12 pi. So this is how you do multiplications and divisions if you already have the polar representation for the complex number. Now, the key thing of this is this theorem, which we're not going to prove, but we're going to write down the statement of the theorem. So this is called the Morph Theorem. It's French, obviously. So not 100% sure it's called the Morph, but I think it's called the Morph. All right, so this is called the Morph Theorem, which says that if you have a complex number and this is the polar representation, and if you raise the power of that complex numbers to n, what you need to do is very simple. You don't have to do very complex computations. What you need to do is to raise the power of the modulus to n, and then these arguments, you just have to multiply with n. So what it says is that if you have z like this, your z to the power of n is nothing but r to the power of n, multiply cosine n theta, and plus I sine n theta. So this is just multiple of the angle theta. And this is going to be very powerful when you use to compute things like this. So imagine if you do not have that theorem, even like if you square this, it's still manageable. So you know that we'll have to write this thing out, and then we'll have to distribute the usual way. So this. But you will see that if you have to use this to compute 1 over 2 plus 1 over 2 to a power of I and raised to a power of 10, this is going to be a mess. This is going to be a mess if you distribute it. But the Morph theorem says that you don't really have to do that. You can, you have an alternative. The alternative is to write 1 over 2 plus 1 over 2i in its polar form. You write this in its polar form, which is here. So figure out what is the magnitude, what's the modulus, which is square root of 2 over 2. Figure out the angle. The angle is pi over 4. So once you have this in the polar form, so if you raise this to the power of 10, you will raise this to the power of 10, which is this. And here you don't raise it to the power of 10, you multiply 10. That's the reason why you have 10 over 4 pi. And then you have 10 pi over 4. Sorry, not. So it's 10 pi over 4, 10 pi over 4. This is what happened when you multiply 10. This is what happened to this angle if you multiply 10. Now, if you do these computations, the new modulus is going to be 1 over 32. And the angle here, cosine phi over 2 pi is actually 0, and sine phi over 2 pi is 1. So that is how you get 1 over 32i. So you can see how the Morph theorem is pretty powerful. It can help you to do a computation like this pretty easily. Now, same thing with the second example here. If you see a question like this, you know for sure that you are not going to distribute them 17 times. So the first thing you need to do is to write these complex numbers, the one that is inside of that power. You write these complex numbers into its polar form. So the way you write into the polar form, you'll realize that the modulus of this complex number is actually 1. And this thing here, if you remember, the way we do it is to put it in the Argand diagram, and you will see that it is in this 4th quadrant. And we're going to use this angle as our angle, and you will figure out that that angle is actually pi over 3. Negative is because we are moving clockwise. So this complex number is 1 over 2 minus square root of 3 over 2i has this polar representation. So if you raise it to the power of 17, the modulus, which is 1 raised to the power of 17, is just 1. And then this angle here, you will multiply 17. You multiply 17 to this angle. That's how you get this. If you are not very familiar with all this, you can use a calculator and figure out what this angle is in terms of degree, and then you keep adding 360 degree until you get some very familiar angle that lies between 0 and 360. And you will see that actually cosine of negative 17 over 3 pi is the same as this. And the sine negative 17 over 3 pi is the same as this. and this will give us 1 over 2 plus square root of 3 over 2i. And as you can see, it is very powerful to use the Morph theorem to do computation like this. Now, the main thing is actually not this. The main thing is that we can use the Morph theorem to compute roots. So, if you remember, so in high school, so if you are looking for root, okay, so if you are looking for the number 1 and you're looking for the roots of this number, so this is basically same as asking what is the number such that you square it is equals to 1. And you can see, maybe you don't do 1 in high school. So let's say we are looking at 4 and then looking at this root, right? So you know that this answer is 2. And because this is the number such that if you square these numbers, this is the number such that you square this number, you will get 4. Now, and here we are trying to say is that if you are allowed to use complex numbers, we have something which is very powerful. It's a theorem given by Gauss. It's called the fundamental theorem of algebra, which says that if you have a polynomial in Z, if you can allow yourself to use complex number, and that polynomial have degree n. So let's say that this is our polynomial. This is our polynomial plus dot 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 plus a1z plus a0. Now, Gauss say that through this fundamental theorem of algebra, it says that if you have a polynomial of degree n and you allow yourself to use complex numbers, this polynomial have exactly n complex root. So this is something which is pretty powerful. So for example, let's say fx equals to quadratic equation x squared plus 1. Now we know that this equation doesn't have any real roots, but if you can allow yourself to use complex numbers, we know that this functions actually have 2 roots because it's a polynomial of degree 2. So same thing here. If you have fx equals to, I am just randomly giving you this polynomial of degree 3, we know that this type of polynomial of degree 3 have at least 1 real root, but it might have 3 real roots. It's a mess. You don't really know. We know that we have 1 real root, but if you allow yourself to use complex numbers, so x here, if it's not restricted to real numbers, if you can allow yourself to use complex numbers, in fact, we know from the theorem of Gauss, you will have exactly three complex solutions, complex roots. So right here, we can actually use this observation that we have from the Morph theorem to compute all the roots for complex numbers. So we can, in fact, compute all the roots for complex numbers, and this is the way we do it. So this right here, so this is what we want to do in this section. We want to find all the n roots for complex numbers. So this is a definition for a root. So an n roots of a complex number z. So you have a complex number z, and you want to find the n roots, okay? So it is the same as finding the complex number w, such that w to the power of n is z. So for example, if you are looking for the root, okay, so you're looking for this thing. Traditionally, this is how we write it, and we want to look at what this thing is. Well, we know that it will have 2 roots, and the roots will be a complex number such that if you square that complex number, it will be z. Okay, so which means that let's say all real numbers are complex numbers. So for example, we can apply this to, let's say, 4. So 4 is a complex numbers. If you want to find the second root, so it's the power of 1 over 2. So in order to find this, we are looking for a number. We are looking for a number that if you square it, you will get 4. And we know there are 2 answers for that. The answers is going to be 2, right? If you square the 2, you will have 4. And if you square -2, you also have 4. So these are called the 2 roots for 4. So 4 to the power 1 over 2 will have 2 roots. Okay, the roots are defined as given as 2 and -2. and if you are looking for, say, for example, the number 1. So the number 1, if you look for the third root, so you are looking for, what is this? So which means that you are looking for a complex number such that you cube them, it will be 1. Now, we know that if you only allow yourself to use the real numbers, then there's only like one real numbers that will work, which is 1. But if you allow yourself to use complex numbers, we can actually find 3 complex roots. 3, which means we can find 3 complex numbers. Let's call it W0, W1, and W2, such that W0 cube will be 1, W1 cube will be 1, W2 cube will be 1. So we will have 3 different complex roots for this, which is like, whoa, really? Okay, yeah, I mean, like, if you restrict yourself only using only real numbers, you know that there's one real root, which is 1. But you allow complex numbers, you can actually have 3 complex roots, which is fun. So we are trying to derive, so right now, we are trying to derive a way to find all these roots, okay? So that's the objective here. So if you look at the book, when they say find the n roots of a complex numbers, this is exactly what we want to do. So if you're looking for the n root for a complex number z, we are basically trying to look for a complex number such that if you raise that complex numbers to the power n, you get z. All right, so let's look at how this is done. And then that is almost the end of these sections, right? So because of these definitions and because we are trying to find, so we want to try to find w such that wn is equal to z, right? So suppose we let w as these complex numbers, which has this modulus s, and then the argument of this complex number is phi. So you have w equals to s times cosine phi plus I sine phi. And then z will have this modulus r, and then the argument will be theta. Now, the Morph theorem says that if you want this to be true, which means that because w is like this, so the Morph theorem says that if you raise this to the power of n, you are doing nothing but raising the modulus to the power of n, and then you take the angle, the argument theta, and multiply it by n. So this w to the power of n is nothing but this. And then if you want to set it equal to z, and this is your z, so you would want to have these equations. So if you want to have this equality, then you better make sure your Sn will be r. That will give us S equals to r to the power of 1 over n. And for comparison reason, if you want this equality to hold, you will also better make sure your cosine and phi will be equal to cosine theta, and your sine and phi will be equal to sine theta. But because sine and cosine, they all have 2 pi periodic, they are 2 pi periodic, so n5 will be actually theta, okay, that theta plus 2k pi, right? Because in order for this to be the same, you can have it n5 equals to theta, or you can have it n5 equals to theta plus 2 pi plus 4 pi, and so on and so forth, 2 pi periodic. So if you solve this for 5, you will see that your 5 is equals to this over n. Okay, nothing very complicated. This is pretty straightforward. So if you want to find a w such that wn equal to z, your w was going to be in this form. Now, your k here is for you to choose from 0 to n minus 1. When you are more than this angle, when you are more than this value, it will just simply repeat itself. So you will not getting anything new. You only get the repetitions. If you get k, if you go beyond n minus 1, if you do k's and n plus 1, so on and so forth. So in order to get n distinct roots, you just have to run this, and you will get all those roots. So, for example, let's do one computation, okay? Let's do one computation, and this is the formulas we use to find roots. So this is the formula we use to find roots. Okay, so how do we apply this? So, for example, you are given a complex numbers. So a complex number is -1 to the -1 plus I, and you want to find the cube root, okay? Which means that you want to find all the w such that w's cube will equals to -1 plus I. So how do we do that? Well, first, in order to apply these formulas, we will have to figure out what is the polar form for this original function z. So write this into a polar form. So this is the polar form, this is the modulus, that's the angle. So in order to find the omega, I call it w. So in order to find w such that w cubed equals to 1, we know there are 3 of them. They are known as w0, w1, and w2. So the formula is given by this, all right? So if you compare and contrast, so that theta, so n right here will be 3 because we are looking at cube root. So this will be 1 over 3. Now what is theta? So theta right here is the argument for your z. So you have to find this. And then you will take that angle that you found, which is the argument for z, and then keep adding this over this, all right? So you found this. So this is the modulus. So this is the modulus, the polar form for z, and this is the modulus. You will have to take 1 over 3, and that's the argument theta. So this is the theta, this is the n, which is 3, and then you have plus 2k pi. So you do this, you take first one, you will take k equal to 0. So you take k equal to 0, this will be 0, this will be 0, so this will give you pi over 4. This gives you 2 to the power 1 over 2 raised to the power 1 over 3, so this will be 2 to the 1 over 6. That's how you get this. And so these two angles will be the same, so you have pi over 4 and pi over 4. And then for k equal to 1, you will get another one. So if k is equal to 1, you will have to do the argument. Will have to be 3 over 4 pi plus 2 pi over 3. So if you do this computation, you will get 11 over 12 pi. And then this will give you another distinct answers, where this thing, if you raise to the power of 3, it will be minus 1 plus I. You can double check actually. If you power this thing 3, we know how to power this. If you raise this power 3, the Morph theorem say this will be raised to a power of 3. Then you have to multiply 3 with this angle, and you will see that you will get back to that. Okay, so this is a second distinct root, okay, which we call W1. And then finally, you take k equal to 2. So the angle here in terms of this argument will be 3 over 4 pi plus 2. So 2 times 2 is 4. So it's 4 pi over 3. And then you will get this angle. So if you go beyond that, if you do k equal to 3, you will get back to this. K equal to 4 will get back to this. So there are no distinct roots. And you know theoretically by Gauss theorem, if you are looking for cube roots, you will have 3, exactly 3. And these are the exactly 3 cube roots. Now, this one, if you put it in our Argand diagram, so this is going to be our omega 0. And this is going to be our omega 1. Sorry, I call it W. So it's W0, W1. And this is our W2. So the roots will be on a circle, in this case of radius 2 to the power 1 over 6. So it will be on the circle. Okay, so if you want to find a cube root for these numbers, all the cube roots will be on this circle, and they all have this angle. So they are kind of equally spaced. So you have this angle, and then plus another angle to get all this root. So this is how you compute the third root of these complex numbers. Okay, and let's apply this to something which is very easy. Let's say in this case, we want to find what is the 8th root of 1. All right, so what is the number if you multiply it 8 times, it will give you 1. Now, if you restrict yourself only, if you think of it only using the real numbers, now we know the numbers is 1 and the number is -1, and we cannot find anything else. In terms of real numbers, these are the only 2 real roots. But if you allow yourself to use complex numbers, we actually have 8 different roots for this. We have 8 different roots for this. Now, this is the one that I get from internet because I'm lazy to draw this thing. My circle is not good. So they are using a little bit weird notation here. So for this, in order to understand this, you just have to get rid of all the 8. And then instead of subscript, you just have to look at the superscript. So which means here, this is W0, this is W1. So you get rid of this. This is our W2. This is our W3, W4, W5, W6, W7, and W8. All right. So that's how you read this diagram. But anyway, if we want to find all the roots, I mean, if you use the real numbers, you can only find 2 real roots. But right now, if you allow yourself to use complex numbers, I promise you we can find 8. All right, so how do we find them? So first of all, treat your 1 as a complex numbers. Your 1 is a real numbers. Real numbers are complex numbers. We talked about this in the first video already. So you write this in the polar form. So the way you write into a polar form, you have to find the modulus, which is obviously 1. The angle theta. Well, in the Argand diagram, the 1 is right here, right, on the real line. So the angle theta, the argument will be 0. And then obviously this is this. You can clearly see that this equality is true, right? So we can write our 1, our real number 1, in polar form. We can do that too, which is this. Now apply our root formulas. So in order to find the root, our theta here is 0. Our theta here is 0. Modulus is 1. And because we are looking at the 8 roots, right? So the n root, so that 8 root, so that will be the 8. And we will run from 0 all the way to 7. Okay, so W1, the first obvious root that we know, will be our k equal to 0. Okay, so in fact, we have the first root, the one that we know. The first root is here. And then we actually have a complex root, which is this one right here. So this is by taking k equal to 1. So you have pi over 4. And these are special angles. So you figure out this is this. Now, if you don't believe me, if you take square root of 2 plus 1 over square root of 2i raised to the power of 8, you will get 1. You will get 1. All right. And again, we don't distribute. Remember, when we do this kind of questions, the way you do it is to put it in the polar form, and you can see we have that polar form. Imagine that we multiply this, raise this power 8. This will be multiplied by 8. So you have the 2 pi. And then you have a 2 pi's. This is 0, this is 1, and you get 1. So this thing here, if you raise it to a power of 8, you do have 1. So we actually do have a complex root right here. So if you're looking for the root, right, we do have a complex root right here. Okay, so not just only this, but we also have it here. This is the weird part. So we also have it here. Now apply this theorem one more time. Now k equal to 2. You actually have another root right here. So this is another root. Okay, and then you apply k equal to 3. You have another root. K equal to 4. You have another root. K equal to 5. This is another real root that we know. And then k equal to 5, we have another root. K equal to 6, we have another root. K equal to 7, we have another root. You actually complete the circle, and every time if you got k is go beyond 7, it will just basically repeat itself. So 1 to the power of 1 over 8. Okay, we actually have 8 distinct complex roots. Roots means complex number which you raise to a power of 8 will give you 1. So this is the one which is kind of like mind-blowing, because last time in high school, when you do not know what complex number is, you know that we only have 2 different roots, right? If you allow yourself only to work on complex numbers and you're looking for what are the numbers that you multiply 8 equal to 1, you can only find this is one of the numbers and this is one of the numbers. But if you allow complex numbers, you actually have 8. There are many reasons to show that the complex numbers is actually the number that we want, because once we have the complex numbers, we have a lot of theorem, very nice theorem like the one that's shown by Gauss, which says that if you have a degree n polynomial, you will have exactly n roots and complex roots. If you drop the complex and only allow yourself to work on real numbers, you don't have that result. And this is not the only thing that we, the reason why we study complex numbers. We actually have an entire course running calculus on complex numbers. So we'll be integrating complex function, dz. This is something special. If you're in engineering, you will see that. In math, we actually have a 400 level class on complex, actually 332. So math 333, sorry, math 333 have a big portion of doing calculus on complex numbers. So some computer science students take 333 instead of 332. 332 is the one I'm teaching right now, which is linear algebra. 333 is some complex numbers and then some linear algebra. So there are many reasons to work on complex numbers. This is one of the reasons why we show you that if you allow yourself to use complex numbers, you'll have a very nice result on roots, for example, okay, on the number of roots for a polynomial of degree n. So this is one thing. The way to apply all this thing is not super complicated. Just make sure that this is how you apply it. make sure you know what all this thing means and how to apply it. And you look at one of two example, you will know this is actually pretty simple. You will know what to do with it. Now the last part here of this sections is not technically not a chapters, it's just an appendix in the book, but we decided to put it as something that you should know in Calc 2. Now, so the last thing we want you to know, there are actually a lot of things. This is actually a course, all right? You can actually take a course on complex numbers, just on complex numbers, the calculus on complex numbers. So we actually haven't talked about how do you define sign for complex numbers. Say, for example, sine 2 plus 3i. What's that means, right? We also have e. So e 3 plus 2i. What does it mean? Actually, we know how to deal with this here. This is what one of the things we want to talk about. But we can do a lot of stuff on complex number. For example, we unfortunately we don't have time to talk about this, but we can also talk about what is the numbers I raised to the power of I. What is this, right? We can also talk about a lot of stuff. So 1 plus 2i raised to the power of 2 plus 3i. What is this? Right? So we don't talk about all this thing because this is just a very brief introductions, and this is also, as you know, very end of the semesters. So one last thing we want to impress upon you is the concept of a complex exponential. So the thing is, if you remember how we define these exponential functions using series representation, you remember the Taylor series and Maclaurin series that we learned? So this is like one of the easiest series representations. That's basically like the first Taylor series that we saw. And I'm telling you that these series expansions also hold for complex numbers. All right, and also not only that, this kind of algebra properties also hold for complex numbers, complex exponential. So we have everything is the same. Basically, substitute all the x with the z, and you can play with the complex number that way also. Now, so if you use that, we can. The thing here is this particular example here is we want to talk about instead of a general complex exponential. We're just going to look at what happened if you have EI theta. So what is the meaning of e raised to the power of I theta? Right, so we apply these Taylor representations for this complex exponential. So now you substitute your z as I theta. So iy, in this case, you substitute your z and iy into these expressions. So you will have 1 plus the iy plus the 1 over 2 factorial over iy squared, so on and so forth, right? Nothing but just substitute. So once you substitute, you also realize that if you have I and you square them, that's -1. And if you cube them, it basically is square and then times this, right? So this is negative, so you have negative I. That's what you see right here. So if you do I to the power of 4, there will be I squared times I squared. So I squared is -1. So -1 times -1. So this is 1. That's how you see this. And I to the power of 5 will be I. You will see we have a pattern that fluctuates between -1 to -I to 1s to I, then to -1s to -I, so on and so forth. So if you expand the complex exponential, this is basically substitutions using the z as iy, and then you will get this, okay? This iy, the I still stay, but this I is gone. Instead, you will introduce a negative. Here, the I cube. So here you have I cube, which is -I. I is here to stay. I to the power of 4, I will be gone. You will have +1 instead, so on and so forth. So you have a part of these expressions which is entirely free of I, and you also have a part of this expression that has I on it. So you regroup them. You group the things that has no I on it, and you regroup the things that has I on it, and you will see this is what you get. Now, if you still remember from our Taylor series expansions, this part here is actually our cosine of y. Okay, now this is not complex number now. So this part here, the I here is the so-called imaginary numbers. I squared equal to -1. Remember when we write iy, the y is a real numbers. So this is your real number. So y is a real number. So your y here is a real number. Oh, So your y here is actually real numbers. So actually this is a real series. This is a series that has nothing to do with complex numbers. Inside here, this is also a series that has nothing to do with complex numbers. So these are traditional real numbers power series. And this traditional real number power series, if you remember, is your sine y. Okay, this is the one with odd power 1, 3, 5, and then you have plus minus plus minus plus minus. This is the odd powers. This is the even power. That's the cosine functions. You have power 0, power 2, 4, 6, 8, and so on and so forth, plus minus plus minus. So this part here is actually cosine y. This part here is actually your sine y. So apparently, if you do EIY, this is what you get. It's cosine y plus I sine y. This is also sometimes known as the Euler's formulas. Okay, so Euler's, remember the Euler's, we talk about that. We talk about his story multiple times in class. And so once you have the EI theta defined, so EZ will be easier now, because if your Z is X plus IY, remember your X is the real numbers, your Y is the real numbers, so this is EX times EIY, and we already know what EIY is, so EIY is cosine Y plus I sine Y. So we have this particular formulas right here. So this is one of the formulas for e to the power of Z. So one example is that if this is your Z, right? So this is nothing but e negative 1 times ei pi over 2. So this is real numbers, 1 over e. And this part here is cosine. So your theta is pi over 2, okay, plus I sine pi over 2. And because cosine pi over 2 is cosine pi over 2 is 0, sine pi over 2 is 1. So this thing here, the complex exponential, e raised to the power of 1 plus I pi over 2 is this numbers. So that's how we apply it. So this is how we apply these formulas. We have to first figure out what is EI theta. Once we have EI theta, we would know what is the formula for EX plus IY. So EX plus IY is EX times the EIY, which is cosine of Y plus I sine Y. So this is also the part which is this is a part which is surprising, because the complex exponential actually involve the real function cosine y and the real function sine y. Now, some of you have seen this formula before, but if you apply it very specially, if you look at this thing here, the complex exponential, if you apply it to x equal to 0 and then y equal to pi, so you're looking at a complex number which is of this form. So we know that e raised to the power of 0 plus I pi, which is our ei pi, will be cosine of that angle pi plus I sine of the angle pi, which is right here. And cosine pi is -1, sine pi is 0. Right, cosine pi is -1, sine pi is 0. So you have ei pi equals to -1. So ei pi is actually equals to -1. And if you move this thing around, you will have ei pi plus 1 equals to 0. Now, this is a formula that people write books on it. Okay, they call it the most beautiful formulas, the top 5 most beautiful formulas in the world, and all that. The reason why it might not look very special for you, but the reason why this is special and people write books on it is because I can send you a video link if you want to. There's a very interesting talk about these formulas. So I is a very special numbers in mathematics. I is the one that gives us complex numbers. I squared is equal to -1. Now, obviously, pi is also very special numbers. E is a very special numbers. Now, 1 is also actually a very special numbers. The reason why 1 is a very special number is because 1 is what we call the identity in multiplications, which means that 1 times any numbers is going to give you that numbers. So this is an identity in terms of multiplications, and 0 is also a very important numbers because 0 serve the same function as 1, but 1 is a multiplication identity and 0 is addition's identity. Addition identity is in the sense that 0 plus any numbers is equal to that number if you use plus. If you use multiply, you need 1. 1 times any numbers equals to that numbers. So they kind of serve the same purpose. So 0 plus a number will get back that number. So in terms of addition, 0 is the one that is serve as an additive identity. And then in multiplications, 1 is the one that serves as a multiplicative identity. So 1 and 0 is also very important in mathematics. And you have 5 very important numbers in mathematics: I, pi, e, 1, and 0, and they all related by one formulas. That's the beautiful part. They are related by one formulas, and that formulas is this Euler's formulas. So again, it's Euler's again, right? So it's Euler. This is Euler formulas, and this Euler formulas is the one that give a lot of people freak out on it. If you Google Euler's formulas tattoo, you will see that. I mean, I'm not putting it here because I'm not sure about all this copyright issues. But if you Google Euler's formulas and tattoo, for example, and you look at the picture, if you do a photo search, you will see that people just put all that formula on their body, and this is considered as one of the top most beautiful formulas in mathematics, is because it's actually very surprising. If you allow your exponentials to be defined on complex numbers, and you actually have all these relationships, all these 5 most important numbers in mathematics are all related by one formulas. So the whole point of showing, actually the books also do it the same way. I mean, the reason why the books talk about complex exponential is because the author, James Stewart, cannot help himself but to tell you that, hey, we have these formulas. So this part here is basically to try to tell you that, hey, we have these formulas. It's called Euler's formulas. Got it? Happy? Okay, so this will be the end of this lecture, and in fact, these 2 videos will constitute the entire sections you need to know on complex numbers. So we will say more about it on Wednesday. I will post this 2 videos, and I will see you on Wednesday, and no class tomorrow. All right, that's it. Good night.